Hello all of you. Welcome to the 36th lecture on the course on analysis and modeling in chemical engineering. In this week, I will talk about graph theory and how it is used in chemical engineering, and I will continue to do that in the following week as well. I will first see like how the graph theory is applied on flow sheets, and then we'll discuss some of the basic concepts of graph theory and how we can then use it in our scheme of like whatever we have discussed. And then in the next week, hopefully, we can see like how we can use this graph theory in rather abstract way in order to solve a system of equations, not really solve it, but to define or develop solution schemes for solving those equations, right? So I want to basically apply graph theory in both these ideas. The first idea is to analyze a flow sheet and to solve, let's say, material balance problems. And the second idea is to basically solve a system of equations, right, which is what we eventually get in any process model. So let me begin, right? I already have told it long back in the course that every flow sheet that you have is essentially some kind of a graph, right? So I told you that when I have a chemical engineering process, there are two things which are very important. One is what is it composed of, that defines my subsystems or the units of the process, and how those units are interconnected, right? So let's say I'm looking at this particular process. The details are not very important here, but let's say some feed is coming and it is coming into a mixer, and some recycle is also coming from somewhere else, and I will come to that. And then the feed plus the recycle is going into a chemical reactor, and clearly there is going to be some product being formed plus whatever is unreacted, and I want to separate out the product. So I get the product separated from here, and whatever is the unreacted part, of course it is never a complete separation, but unreacted part I may want to recycle, and then the product maybe I want to dilute or whatever. So I basically want to mix with, let's say, something else. Let's say my goal is to make it more dilute than whatever we have got, and then we get the final product, right? So clearly this process is going to require equipment, the mixing equipment, the reactors, the separator, and the mixers, right? That's already we have discussed how to model chemical reactors, how to model, let's say, uh, the heat equation we have discussed, like how do we see the temperature distribution and things like that. And in the following classes, in couple of weeks, we will also discuss in more detail how separators work. We already have discussed evaporator, that is one kind of a separator where we get complete separation to some extent, right? But we will discuss more about distillation columns and things like that. So we already have discussed how the different units work and how do we model that. But let's step back a little bit and just look at this flow sheet. There is also one more piece of information that is very, very useful, and that is how they are connected together. And in fact, whatever system of equations that we get in the final model, whatever we form, is of course going to depend on what the units are, but they are also going to depend on how they are connected together. And in fact, the nature of the coupling between the equations of, let's say, reactor and separator in this particular example is going to be determined a lot by this interconnectivity in the flow sheet. And therefore, we should have mechanisms to interpret and analyze the interconnectivity in more detail, because this is going to have a bearing of the solution of whatever model I am going to build, right? And fortunately for us, there is a well developed apparatus of graph theory. It is not only for chemical engineering, that we can employ in order to analyze this interconnectivity in more detail, and we will see what purpose it serves in simplifying or in basically helping us solve the model that we eventually get for the entire flow sheet, right? This is the whole idea here. So what I do is basically I can represent this kind of flow sheet with a graph, and henceforth I will not be discussing the flow sheet always, but there is a graph. You can imagine that it's a flow sheet, but what I am discussing, at least in this class and the following couple of classes, is just an abstract notion of a graph that need not be a chemical engineering flow sheet. It can be any graph for whatever reason, right? So in this particular case, we have 4, I can say, nodes, right? So this 1, 2, 3, 4 are what I call nodes, or I can also call them my units. I can also call them vertices. I will typically call them vertices in many cases here, and they are connected together by this red things that you see here. These are my edges, right? These are my, all the red lines you see here, they are my edges. Edges define how the nodes or vertices or units are connected together. And now there are some nodes which are internal to the system. What do I mean by internal? Is they are not getting any feed, or it is not getting any output directly outside the process. Let us say the reactor in this case, right? So every input to the reactor is internal to the system. It's not getting a direct feed, right? And every output is also internal because the product is processed later after it comes out of the reactor before we get the final product, right? So anything which is not connected to a direct input or output is the internal node, and accordingly we have input interface and output interface. So let's say one here, the mixer is getting the fresh feed, and this is therefore characterizes the interface. It's how the input comes in the flow sheet, right? And one is called therefore the input interface. 4, we are getting both input and output, so it is input and output interface, right? And what you will see for most examples I will do, I will, at least in the today's class, I am going to not worry about the interfaces, because interfaces are something probably we know the feed flow rate, we know the product flow rate, those things are known. We are focusing more on just the things without them, right? So I basically drop these 3 edges, and now what I am left with is simply this graph that essentially represents how the units are connected together without worrying about the interfaces. Of course, the interfaces are important, and we will get back to cases where we will see like how we can incorporate the effect of interfaces. But in the beginning, when I define graphs and things like that, I will take a general notion of graph that is something like this, except the interfaces. All right. So how do we define a graph? So a graph, I can call it some G, is in general some collection of vertices V, some kind of a set of vertices we can say. Let us say here V is a set of 3 vertices, V1, V2, V3, and lines joining the vertices which are called edges, and again E is also a set of the edges. In this case we have 2 edges, E1 and E2, and together this V and E constitute the graph G, right? Now the vertices, as I said, it can be units, it can be nodes, it can be points, it can be elements, it can be a system. The idea that we are discussing right now is not specific to chemical engineering. This is how the graph has been, graph theory has developed. But since the context in which the graph theory is applied can be different, the vertices may mean different things in different contexts. The edges accordingly can also mean flows, streams, or sometimes a simple relationship between the things, right? What you also notice here is when I draw this particular graph, I did not define any arrow, right? That means I am not saying is going from where to where, right? When I define the direction of the arrow, that means I am probably representing some flow or stream. Then what we have is basically a digraph, right? So the only difference from The graph above and graph below is like, in this case, the direction of edges are specified, which is what we will use almost entirely in this course, right. So, this is a graph with directed edges. Since we are eventually interested in chemical engineering kind of an application, we will only deal with digraphs, which are graph with directed edges. So, henceforth, when I say graph, I am basically restricting myself to digraphs, right. There are cases where something without edges can also be there. Let us say, for example, I want to have the graph representing a family structure, let us say father, son and mother. Now, they are interrelated and the edges may define the relation, but then it is not like a one-way relation is both ways, right. So, there is need not be any direction if, let us say, I want to use graph to define the relation. Or let us say your Facebook friends, you are friends with someone and he is also friends with you, he or she. So, that is a relation. There need not be any one-way communication from one to the other, right. But we are restricting ourselves to cases where the graph theory is applied with a defined direction for the edges, right, which is what we call a digraph. Okay. Now, there are a few more definitions. There is something called a simple graph, and pretty much all the graphs that I will discuss in this course are going to be simple. This is a graph which is having only one edge between two vertices. In principle, you can have more than one edges between two vertices. There can be multiple kinds of relations between two vertices. What I am showing here, for example, between V2 and V3, there are two edges, E2 and E3. And in fact, you can imagine something like this in a chemical flow sheet as well. You can have two units that is exchanging mass between themselves and also energy between themselves. So, there is a flow of mass, flow of energy, and I can, if I am representing the edges as mass flow and energy flow, I can define multiple edges, right. So, there are cases in chemical engineering as well where we can define non-simple graphs, but I will restrict myself for simplicity to the simple graphs only, except and I will discuss something called a self loop, right. But that again is like again a simple graph, but there is a loop to the same vertex where it comes from, right? But I will discuss that case as we come there. Okay, few more definitions. There's something called finite graph. I mean, in mathematics, everything has to be defined with respect to finiteness. In principle, we can have infinite number of vertices and elements, but for all we care, for all the applications we are interested in, we are interested in finite number of edges and vertices in my graph. And finally, this is something which is most important for us, as we will see, is this idea of a acyclic graph and a cyclic graph. Acyclic graph is a graph with no directed cycles. Whenever we have a directed cycle, we have something known as cyclical net, the other name for the directed cycles. What does it mean? In this case, for example, 1, 2, 3, and then we go back to 1. So, let us say I am thinking about a flow of something. So, it can go from 1 to 2, then 2 to 3, then 3 back to 1. So, basically I can revisit the same vertex if I am going along this graph. I am forming some kind of a loop within the graph. So, whenever a loop like thing is being formed, what I call directed cycle, in that case I am going to have a cyclical net and the graph is no longer acyclic, right, when we have a cyclic graph. Now, you can see very clearly what does that correspond to. In this case, we have a recycle. I have told you that I am doing in an abstract manner, but if you have to apply to chemical engineering, this is going to apply for recycle streams, right. There may be things that may look similar to a loop, but it is not a loop, and that is, for example, the bypass stream in chemical engineering. So, let us say I could have also had a very similar graph 1, 2, 3, where I have something like this. It looks like a loop, but it is not directed. The reason being, I can go from 1 to 3, I can go from 1 to 2 and then to 3, but then I cannot come back to 1. There is no loop here, right. So, there is a direction of the edge from 1 to 3 is now 1 towards 3, not vice versa as we had here. So, it is not forming a loop. So, it is not cyclical net, and this is pretty much a acyclic. This is pretty much a acyclic graph, right. So, we will take some examples more on this, and what you will see that whenever we have cyclical net, the graph becomes more complicated, and in fact, the number of cyclical net and the complicated nature of cyclical net is what defines the complexity of the graph and things like that. We will get to that point as we get there. Now, here start coming the actual beauty of the graph and why it is used a lot in computation and things like that. The point is that every graph I can represent using a matrix, right? And then computers know how to deal with matrices. There are algorithms out there. We just discussed some of those algorithms in the previous week when we discussed the numerical methods, right? So, we can represent every graph by something known as a Boolean matrix, right? For example, the graph which I have just shown earlier, I can write a Boolean matrix for this graph. That is what you see here, 3 by 3 matrix. This is my R, and I have put some labels. These are labels, these are not part of the graph. I have put some labels, they are not part of the graph, just to indicate what this matrix indicate, right. So, these indicate essentially whether there is from a certain vertex to a certain vertex, right. So, along the rows I see like where it comes from, and along the columns I see where it goes to. For example, there is an edge going from 1 to 2 in the graph. So, I take the first row, that is from 1, it is going to 2, and then the corresponding element I have in the matrix is this, and I put a 1 there. 1 means that there is a flow from vertex 1 to vertex 2. And which element is this? This is the first row, second element of the matrix. In general, I can say that my Rij, that is ith row, jth column, that element is going to be 1 if there is a flow from vertex I to vertex j, and when there is no such flow, I will put a 0. Let us say from 1 to 1 there is no flow. From 1 to 3, you can say I can go from 1 to 2 and then to 3, right, but I am looking at direct edges. So, there is no direct edge between 1 to 3, or in other word, there is no one step path, from 1 to 3. I can get there in 2 steps, and I will come to that how we can get that as well from the graph theory, but we are looking only at 1 step path. So, in 1 step path or direct edge is only between 1 to 2, and then for 2 similarly there is a edge from 2 to 3. So, I put a 1 there, and 2 to 1 and 2 to 2 there is no edge, and then finally from 3 there is an edge to 1. So, I put a 1 there, and now I form a 3 by 3 matrix that is called the Boolean matrix for this graph. Now, I can use this Boolean matrix to construct the graph, or for every graph I can map a corresponding Boolean matrix. The Boolean matrix is pretty much a unique signature for whatever graph that we look at. Okay. The elements of this Boolean matrix, the Boolean matrix by the way are also called by other names like adjacency matrix and things like that, but I will call it a Boolean matrix just to indicate the elements in there are following Boolean arithmetic. What does it mean by Boolean arithmetic? Is that whenever I have to add two numbers, I will not add in the routine way like 1 plus 1 becomes 2, but I will say 1 plus 1 is the maximum of 1 and 1, whatever is the maximum number between 1 and 1, and therefore, that becomes equal to 1. Similarly, 1 plus 0 is maximum of 1 and 0, that is equal to again 1. By the way, that is the same answer we get by simple addition. but that will not apply in the earlier example. 1 plus 1 by simple addition becomes 2, right? But by Boolean addition, it becomes simply 1. And whenever we have a product, then I take the minimum value of the 2. So, let us say 1 dot 0 is minimum of 1 and 0, and that becomes 0, and 1 dot 1 is minimum of 1 and 1, that becomes 1. That looks like a simple multiplication as well, but just for consistency and the actual definition of Boolean arithmetic, we are going to follow this. So, what this means? Let us say I have this as my matrix, the Boolean matrix, whatever I had just now. If I add another to it, if I do plus, then matrix addition I will do in a similar manner. So, I will add basically term with term. So, this the first term here I will add to the first term here, second term here I will add to the second term here, but each of these individual additions I will not apply simple rules of addition, I will apply the Boolean rule. Let us say second element here is 1, and if I add another r to it, it becomes 1 plus 1 equal to 2 by simple addition, but I will not use that rule. I will take the maximum value of 1 and that is 1 here. And similarly, for the second row, we have a 1 here, so 1 plus 1 becomes 1, and for the third one, again 1 plus 1 equal to 1. Essentially, plus remains equal to in the Boolean arithmetic. R square, on the other hand, is somewhat more interesting. So, if we have R square, then the basic matrix multiplication rule remains same, that means we multiply row with column, but then wherever I am doing multiplication of the elements or the addition of elements, then I will use the Boolean arithmetic, right. So, let us say for example, the first element of the final matrix in R square is 0. So, R square is R into R, and that 0 is coming by multiplying the first row with the first column, as we do in the Boolean, as we do in the matrix multiplication, the normal multiplication, right, and that becomes 0 into 0 plus 1 into 0 plus 0 into 1, and each of these multiplications I will do using Boolean arithmetic. So, this become minimum of 0 and 0, that is 0, minimum of 0 and 1 is 0, and minimum of 0 and 1 is again 0, and 0 plus 0 plus 0 in Boolean arithmetic also is going to be 0, right. So, if I do that, so next similarly I can do for all the elements in the matrix, and I get R square, right, and I can go ahead and do R cube, R4, all the powers of R. And there is something interesting about these powers of R. The powers of R basically contains information on the n step path. Let us say Rn, R to the power n, gives me information regarding all the n step path that we have in the graph. Let me start with this simple graph. So, my R is going to look like the following. So, I am putting some labels here, 1, 2, 3, 4. This is not part of the matrix. This is my from, and then 1, 2, 3, 4. This is my 2. So, 1 to 2 there is an S. So, I put a 1 there. 2 to 3 there is an S. So, I put a 1 there, and 3 to 4 there is an S. So, I put a 1 there, and all the other elements are 0. So, I do not bother to write 0 everywhere, right. So, this is pretty much this 4 by 4 matrix is my R matrix, right. Now, let me compute R square. So, R square is going to look like 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and 0, 0, 0, 0 multiplied by itself, that is 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and 0, 0, 0, 0. And you see what is this going to be? So the first element will come from multiplying the first row with the first column, but first column contains all zeros, right? So therefore, it is going to be 0 here. The second element will come from multiplying the first row with the second column. And now you see I will do a term by term multiplication, but as a trick you can see that only the second element is non-zero here. So if the second element in the column is non-zero, then only we will make anything, right? You can do the full math, but what you see here is if the second element in this row is 1, then second element in the column should be 1 in order to give anything meaningful, right? So if I do a multiplication, we get 0 into 1 is 0, 1 into 0 is again 0, 0 into 0 is 0, and 0 into 0 is 0. That gives me all zeros, right? It would have been 1 only if the second element in the column would have been 1, right? So you see that in the third column, the second element is 1, and you can see for yourself, now we get a 1. 0 into 0, the first elements multiplied becomes 0, but this 1 gets multiplied with this 1, and now I get a 1 here. If any other 1 also comes and get added, it remains 1 because 1 plus 1 is still equal to 1 in the Boolean math, right? And the last one again, the second element of the last column is not 1, so therefore I put a 0. The same rule I apply for the second row here. For the second row, the third element is 1. So wherever the third element is 1, that column is also only going to be important. So now we look along the columns. Third element is 1 only for the last column. So for second row, only the last column is going to have 1. Similarly, for the third row, the last element is 1. So wherever the last element is 1, I will choose from the columns, and last element is not 1 anywhere. So we are going to have 0, 0, 0, 0, and then again 0, 0, 0, 0. And now you see if I do the labeling again, so this is my from 1, 2, 3, 4, and this is my 2, 1, 2, 3, 4. What do we get from here? We are getting, let me list all the elements which are non-zero. So 1 to 3, this is non-zero, 1 to 3 is non-zero, and 2 to 4 is also non-zero, right? 2 to 4 is also 1, 1 to 3 is also 1. And what do this represent on the graph? You can see for yourself, they represent two-step paths in the graph, right? 1 to 3 is a two-step because I can go from 1 to 2 and then to 3. 2 to 4 is two steps, 2 to 3 and 3 to 4. And these are the only two-step paths that we have in the curve, in the graph, right? I can go ahead and compute r cube, let's say. So r cube is going to be r square into r, and r square I have evaluated. And then r is whatever I had at the beginning. And I will apply the same rule of multiplication. For the first row here, the third column is basically non-zero, and third column is non-zero for the last column here, right? So we are going to have 0, 0, 0, 1. For the second row here, the last element is 1. So I look at columns containing last element 1 here, that is not the case. So we have basically all zeros. Then for the third and fourth row here, they are anyway all zeros. So there is a single element that is 1, and that corresponds to, if I label again 1, 2, 3, 4, 1, 2, 3, 4, that gives me a three-step path from 1 to 4, which is indeed the case. I can go from 1 to 2, then to 3, then to 4, right? And now you can imagine if I compute R4 now, R to the power 4, I should get a null matrix containing all zeros because there is no 4-step paths in this particular graph. Okay. So based on this idea, I can now have some kind of a theorem that is generally valid for any acyclic graph, provided that we don't have cyclical nets. For an all acyclic graph, there is going to be some value of n corresponding to the longest path in the graph, such that r to the power n plus m is going to be a 0 matrix for all m higher than equal to 1, right? So in this case, R was a non-zero matrix, R square was also non-zero, R cube was also non-zero matrix, but R4 is containing all zeros because there is no 4-step path in the curve, right? And now you can imagine R5 also has to be 0 because R4 is 0, and if you don't have any 4-step paths, you also do not have any 5-step paths and so on. So basically all the higher powers of R beyond R4 is going to be all zeros, right? So in general, in this case, if I apply this theorem, we are having n is equal to 4, right? So n is equal to not 4, n is equal to 3. So 3 is the longest path that we have. Maximum path is length is 3 steps. Beyond 3, all the powers of R are going to 0. The same is not true if your graph starts to have a cyclical net. We can also define one more quantity. It is called a Boolean sum, and Boolean sum is what we get if I add R with R square, R cube, R4 and R4 and so on, right? So let me go back to this curve and compute different Boolean sums. What is my B1? So B1 is my R, and that represents pretty much all the 1-step paths. Let me quickly write my B1. So we have from 1 I can go to 2, from 2 I can go to 3, from 3 I can go to 4, and for 4 I cannot go anywhere. Wherever you are in doubt, you can always go back and write the labels from and to, right? B2 is my R plus R square. So now I am adding information from 1-step path and 2-step path, and let us see what do we get. We get something like 0 1 0 0, 0 0 1 0, 0 0 0 1 and 0 0 0 0. Now let me add R square to it. R square in this case, from 1 the 2-step path goes to 3, from 2 2-step paths goes to 4, and from 3 and 4 it is anyway all 0, and this gives me something like 0 1 1 0, 0 0 1 1, and then 0 0 0 1, 0 0 0 0, right? So now this contains information from both 1-step path and 2-step path, right? And now you see B3 therefore is going to be R plus R square plus R cube, and you see in R cube we had a single element that was at the corner, right? The 4th element of the first row that gets added here, and what I get is something like 0 1 1 1, 0 0 1 1, and then 0 0 0 1, 0 0 0 0. And now if I add R to the power 4 to it, it is pretty much still the same Boolean matrix, right? So now if I do B4, B5, B6, B4 is going to be same as B3, and that is same is true for B5 and so on, right? So eventually this matrix basically converges, right? this sum, whatever matrix sum we're getting, basically converges. And therefore, I can define something known as a reachability matrix, that is a sum over all this r plus r square plus r cube and so on. Wherever this Bn becomes equal to Bn plus 1, we have pretty much reached this, right. So, B3 equal to B4 now. Now, the matrix is not changing. So, that whenever the matrix stop changing, what we have is a reachability matrix. What does it represents eventually? It represents that irrespective of the number of steps, if there is any path between any vertex to any other vertex, all of that is basically here, right. So, for this case, this is my also my r star, and now you see from 1 I can go to 2, from 1 I can go to 3 in 2 steps, but does not matter. From 1 I can go to 4. If there is any possibility of going from 1 to any other vertex, that is taken care of here. Similarly, from 2 I can go to 3, 2 I can go to 4, and from 3 I can go to 4. That pretty much means whether two vertices are reachable. Can I go from one vertex to any other vertex, right? Doesn't matter how many steps. If it is reachable, then in the reachability matrix, I will have 1, right? And this idea will be more useful as we will discuss in the next class. So, with that, I want to conclude this lecture, and in the next lecture, we will take it further, the idea of reachability matrix, and we will also discuss about cyclical nets and all that. Thank you so much.